Hello again. And as I promised yesterday, I'm going to talk more about grain growth today. The reason I talk about this is not because you are interested in grain growth, I'm sure you are not, but I think it's a very nice example of how array programming can be a superior paradigm. And I'm sure all you think that, but probably you need to convince some other people in your company or in your environment. And yeah, I think this can be a nice example. It's actually based in a true story. These are the conclusions that I got from giving a course on materials modeling at the university. So what we do here, this is a course for material science students. They are master students who are already finishing. They do this in the last semester. And we give them an assignment. They have to choose some modeling problems. So it might be grain growth, maybe phase transition, maybe some mechanical deformation. And then they have to find in the scientific literature some paper that describes a model to simulate that process. And they have to reproduce the results of the paper as good as they can. In this case, the students choose grain growth. I told yesterday about it. What grain growth is a process that happens in polycrystals, in metals in general. And you apply some heat, and then the grains start growing because they try to reach a state of minimum energy. I used this analogy yesterday, this example. It's the same thing that happens with soap bubbles when they merge and they disappear. And then they have to find in the literature some paper to describe a model like this. And in this case, they choose this paper. It's a nice model. It's a bit old, but it's good enough. It's simple. The paper only has 7 pages, which is a very small paper for what we are used to. 30, 40 pages is normal. So it's a relatively simple model. Well, in the model, we have several energies they have to work with. We have a thermal energy in every cell. We will divide the material in different cells in a square grid. And every cell will have a thermal energy which depends in a statistical distribution. It's kind of random, but it depends on the temperature. There is also some boundary energy at the boundary between all cells. And well, they have to calculate it with this formula here. It depends on the misorientation. I talked about misorientation yesterday. In this case, they are not really calculating them. They are just using that simple formula. So for orientations, we use integers. Each cell will have an integer that is the orientation, and that simple formula there will give them the misorientation. And then we have an activation energy. This is just a constant value. And what will happen in the material is that they have some transformation rules. And here, the cell will transform if the boundary energy plus the thermal energy is larger than the activation energy. What this happens here is that, imagine that you have some ball here. And if you put the ball at the top, it will try to reach the minimum energy. But to become here, it needs enough energy to go up and later come down. So those are the transformation rules, and they just need to apply that. So the students do this. They can choose the tools they want, the programming language they want, and they choose Python. The students know Python, and everybody tells that Python is very easy, and it's there, so they use Python. And they write something like this. I won't get into that, but the core of the model is here. This is a modeling step, and you can see that they use for loops, as we have taught them at the end. And okay, they have this model and they try some test problems. A typical one is a random microstructure. So here at the lab, we have our initial microstructure. We just assign a different orientation randomly to each cell. And then the grains have to grow. You can see there at the top in the graph the evolution of the grain diameter, of the grain size. And yeah, grains are growing, so this is fine. Another typical test problem is having only a circular grain. We have it here. And this should shrink and eventually disappear. But this is not working. It's shrinking and disappearing, but at the bottom it's growing sometimes, and it still shrinks towards the center. So it's not working. And why is that? And yeah, you look at the code, and it's not easy to figure out why this is not working. What would be nice to understand why this is not working is to have some partial results. We want to know what is the thermal energy of every cell. We want to know what are the boundary energy that we are calculating. And we want to know if we are doing some mistake there. So, okay, the students modify their code, and what they have to do then is to define all the arrays at the beginning, and then fill them in the loop. Yeah. They do this, and then you can see that the new boundary energies are the same independently of in which cell we transform. And this would be the product cell that we select. We would have different colors for the north, the south, the east, and the west cell. But we see that we are only choosing two of them. There is some error there. The problem is that when the energy is the same, it should be random which one you choose. But here is not random. We are choosing the minimum, and Python will tell you that if all they are the same, that the minimum is the first value that it finds. So they need to randomize this. The way they do this is to put all the cells, generate a random number, choosing one from there, but you can give them a little hint that you tell them, well, we are only using the boundary energies to select one, so why don't you just apply some random perturbation to the energies that you have, and then you select one from there. We add a parameter that is there at the bottom, so we apply a perturbation of a 1%, and then this will be random. Okay, we do this, and then now the neighbor that they choose is kind of random, and they check the results, and it works. So, yeah, they did great. They replicated the model. This is what they have to do. But of course, we asked them to go a bit further. And there are other problems with this model. There are some times that we observe some checkboard patterns. You see here, for example, a single cell, here too. This doesn't really happen in materials, and we asked them, could you fix that? And a way to fix that is to take into account the second-order neighbors. In the other version I showed, they only consider the north, south, west, and east neighbors. But if they also consider the ones in the corners, the second-order neighbors, then they will take this into account. So they modify their code again. And they have something like this with the additional energy. And now the results look quite better. There's still some checked pattern, but more or less it looks quite better. But they have this code. And yeah, this code is not so nice. There is a lot of repetitive code. It's not easy to understand what they are doing. It's easy to do a mistake there because you have to write the same thing again and again and be careful with the indices. Yeah, off by one errors are very common here, and it's very slow. This model is very slow. So the solution is array programming. they could use NumPy for that. With NumPy, you can do array programming, and this is much less code. They will do less mistakes, and the performance is much better. But also, this code is much less likely to be written by our students. There are a number of functions here that they don't know at all that come from NumPy. What's the problem here? That the NumPy is huge. This is the index of the documentation. These are the universal functions they have. They are equivalent to our scalar functions. Then they have all these array types. And then you have all these routines that will be our mixed functions and some other things. So, yeah, my claim is that learning Python might be easy, but mastering NumPy is really hard. It's not something that you can expect from our students. And I imagine you can guess where this is coming. They could use APL. APL is much simpler. At the end, what they need to know is just these few symbols. They look intimidating at first, but I think it looks way less intimidating than all those NumPy functions that we saw. So how can you write the grain growth model in APL? I wrote this one, not the students. But you can write it like that. You can see that is quite small, and this is the whole solution. Before I was only using the calculation of a step, but this is the whole model. Is calculating the solution each step, iterating. I'm also calculating the average diameter here. In the Python code, we are using some external libraries. And here there are no external libraries. I don't even use system commands or anything like that. And the partial results that we wanted are available in the interpreter. They can just look at them. I'm quite sure you can do this in Python, but the students don't know how to do it. Yeah, I know many people don't like code like that, so condensed. The reason I write it like that is not because I like it, so I really like it, to be honest. But I have another version, which is, let's say, a dumbed-down version of the same thing. Here I don't use strings at all. I try to use as few operators as possible. Instead, I use the fonts. I have lots of comments, and this is what I actually use to explain them how to do it. I have all this in a Jupyter notebook. I also have some slides to show them how it works, and so on. But the reason I write it like this is because I want to use it with Py'n APL, and then embed it in Python so that I can use the same visualization tools and compare the results and so on. Something I can do, for example, is to run some benchmarks. So I ran this for that circle problem. And yeah, these are the results. You can see that the Python loop version is really slow. NumPy is doing good. APL is doing a bit better. Then don't take this too seriously, because I'm not really trying to find the maximum performance. The APL version could be faster, and if you run it in the interpreter, it's faster, but I'm quite sure the NumPy version can be much faster too, and you could use NumPy, these kinds of things, and then it will be much, much faster. But what is important here is that we are in the same ballpark. We can reach a good performance. Yeah, there is more or less the results we have. As I said yesterday, I'm planning to modify this model. I'm already working on it, and we will have something more advanced. But well, I will not get into this today. I talked a little bit about it yesterday. And I would like to jump to the conclusions. I showed 4 different versions: Python with loops, Python using NumPy, a very small APL version, and a bit longer version with more comments and so on. And well, we can conclude that the ray programming offers clear advantage. I think it's obvious here, choosing between this at right, one or the other. I think it's a matter of style, a matter of preference. Maybe you want to use NumPy for whatever reason. But I think it's clear that this one, the Python loops, is an inferior solution. They shouldn't do that. We have intermediate results just for free when we use array programming. There is something that I think we normally never point out, but when you are trying to solve a problem, it's something very useful. When you use the loop, it's very difficult to know what's going on, and then you need to complicate your code like we did at the beginning. With array programming, you don't need to do that. Another conclusion is that, yeah, Python is a very easy to know language, but NumPy is not at all. An APL can be a good alternative here for this kind of problems. There are many things that it does great. It's a very powerful language. It's not difficult to develop in APL once you learn, all you know this, I think. It has a high performance out of the box. What I mean here is that it's difficult to write performant Python code, but the APL code that you write is good enough. Normally, you can have a good performance without having to work too much into it. There are also many good tools, mainly by Dyalog, and well, there is a very good community. There are also some things that can be improved. It's not very well known in some circles. For the main experts, it's a bit difficult to get started into APL because, yeah, there is a lot of learning material, but they want material tailored for them. They want something that applies to their field directly. They don't have specialized libraries. Here I could write something to calculate the grain diameter, but many times there are some things that they don't want to write from scratch, and we don't have libraries for it. And well, the community is great, but it's tiny compared with the Python community. It would be great if the APL community would be so large as the Python community. So, yeah, there are some things that need to be improved, but I mean that the language itself is fine. Yeah, that's pretty much it. So, to sum up, APL is great, reprogramming is great, and the students will learn it. Thank you.